In chapter 6, we're going to look at a couple different types of chemical bonds. Okay, can anyone give me like a brief definition of what a chemical bond is? What happens in a chemical bond? Yeah, two things come together, right? That's a chemical bond. That's a very basic definition. I'm going to give you kind of the book definition of it, and then we're going to be able to explore a couple different types of chemical bonds. So the main definition of a chemical bond is a mutual attraction between the nuclei. Actually, I'm not going to even. Between two atoms. I'll leave it at that. That's not even a full book definition, but we'll say it's that. A mutual attraction between two different atoms. And we need to understand really within these two atoms what has to be pulling them closer together. All right, I want you to think about that question a little bit. What has to be pulling them closer together? Or are their nuclei going to be attracted to each other? Right? Because what's the charge in the nucleus? Let's break that down a little bit more. What's the charge in the nucleus of an atom?
Neutral.
Not neutral. It's got protons and neutrons, which means it's got a positive charge in the nucleus. Does that part make sense? And then the electrons of another atom, what type of charge do they have? A negative. So what's really happening is that the electrons from one and the nucleus from the other are attracted, right? And the nucleus from one and the electrons from the other are attracted. It pulls them close together. So that's what happens in a chemical bond, right? We have a mutual attraction between two different types of atoms, or it could be even two of the same type of atom. Okay, there are two main types of bonding, three types of bonding that we're going to study in this chapter. The first of which is called an ionic bond. Okay, we know a little bit about ionic bonds and ionic molecules. What are they usually between?
A metal and a non-metal.
It's usually between a metal and a non-metal because we learned how to name ionic compounds. So it's the same type of thing. Ionic bonds are between a cation and an anion, right? Or you could think of it as a metal and a non-metal. Okay, so in ionic bonds, we can think of them as something between a metal and a nonmetal, or a cation and an anion. We're going to get to ionic bonds a little bit, but I want to talk about the difference between that ionic bond and covalent, which is going to be kind of our big main portion of our chapter here. But in an ionic bond, what happens is a give and take of electrons. Give and take of electrons. Or sometimes you'll hear it called trading of electrons. Okay? What happens here is that one atom or one element completely gives up its valence electrons to another. That one collects those valence electrons and keeps them as themselves. And then they have these charged particles that hang out next to each other. Okay? So let me give you just like a real quick glimpse into what an ionic bond might look like. Okay, let's look at an ionic bond for sodium chloride. All right, here's my sodium atom. How many valence electrons does sodium have? Or it has one, right? Because it's in group 1. What's the charge of sodium usually? Usually it's +1. Okay, so let's just think about its valence electron first. Sodium has one valence electron. We'll just represent it with a dot. Okay, chlorine has how many valence electrons? Look at what group chlorine is in.
7.
Chlorine's in group 7 or 17, so it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7.
Is that how we're going to be showing our electrons?
Yeah, we will eventually get to drawing them like this. But I just want to show you a quick example first. You're not having to learn how to draw it yet, just quite yet, but in a little bit we will. Okay, I want to give just an example of ionic bonds here, right? This is ionic. Okay. How many electrons do they want to be whole, right? To be complete, how many electrons do they want? 8, right? Do you remember when we talked about electron configurations? 1s2, 2s2, 2. They want all of those electrons full. So they want the s orbitals and the p orbitals full. That means 8. Okay, so in this case, sodium, what it does is it just gives this electron to chlorine, right? It just literally gives it away. And so now chlorine has this extra electron from sodium. And so when sodium gives that electron away, what charge does it now have? A +1, right? Because it's down an electron. It's short an electron, right? It gave it away to chlorine. Chlorine has an extra electron. What charge does that give it? A -1. And what happens to a positive and a negative? Do they attract or repel? They attract. And so now this is formed what's called an ionic bond. Right? An ionic bond is really not, they're not attached in any way. The way that they're attached is because they're so strongly positive and negative that they attract to each other and they just hang out really close to each other, and we call it an ionic bond. Right? One of them gives their electrons totally away, the other one takes them. Now they take on these charges that happen to attract each other. Right? And that's what's called an ionic bond. It's not something we're going to focus a lot of our time on. We're going to focus on covalent bonds, which share electrons, and then two of them get to count them as their own. And so those are a little bit more complex. But in ionic bonds, it's a give and take, right? Sodium gave up its electron to chlorine, now resulted in a charge, and now they hang out really close to each other, and we call it a bond. Okay? Yeah.
So if they want 7 electrons to be whole, why doesn't chlorine take the 1 from sodium?
Well, it wants 8 to be whole. So chlorine has 7, so it does. It takes that one from sodium. And sodium giving it away, now it's got a lower shell that's totally full. Okay. Right? So it got rid of that one outer valence electron. So now if you count chlorine's electrons, 1, 2, 3, 4, 5, 6, 7, 8. Right? It's complete. And then sodium got rid of its outer electron, so its underneath shell was complete. So they're both happy. Okay? All right, let's dive a little bit more into covalent bonds. What are covalent bonds between?
2 cations.
Yeah, they're between 2 non-metals or 2 anions. Okay, they're between 2 metals or 2 anions. And what we see here is a sharing of electrons. Okay, we see a sharing of electrons happening. Okay. Now, in these sharing of electrons, in these covalent compounds, very rarely do things share 100% equally, right? When do you think would be an example of a time where the electrons would be shared totally evenly, right? 2 atoms are bonded and they're shared completely evenly. Can you think of a case where that might be true?
2 from the same group.
Perfect. 2 from the same group, but more specifically, even more specific than that,
2
of the same element would result in a bond that is perfectly symmetrical and perfectly shared evenly. Does that make sense? Think of it as like a tug of war. If I have 2 hydrogens bonded, both of them are pulling on those shared electrons evenly, right? They both have equal weight. But if I have a bond between fluorine and hydrogen, they're not pulling on them with even weight. That's called a polar bond. And so when we talk about sharing of electrons, sometimes they're shared equally. Oops. And sometimes they're shared unequally. I don't really know if that's a word, but I'm going to call it a word. Okay. If they're shared equally, this is what is called a non-polar covalent bond. We're going to talk about these a little bit more in a second here, but this is called a non-polar covalent bond. And if they're shared unevenly, this is called a polar covalent bond. Okay, so I hope now that kind of begs the question, well, actually, see, can you come up with, what do you think, where do you think we're going next? What question do you have just based on this information?
What do polar bonds look like?
Yeah, good. That's a good question. What do polar bonds look like? I'm hoping that you're thinking about the question, well, how do we know if they're going to share evenly or unevenly? Right? Was that question formulating? How do we know if they're going to form evenly or unevenly? That's why I gave you that scale, right? This guy right here, this Pauling scale. Okay? The Pauling scale tells us what's called an element's electronegativity. Okay? Electronegativity. So the Pauling scale tells us what an element's electronegativity is. And all essentially you need to know right now for electronegativity is the electronegativity value tells you how badly does an element want electrons.
Wait, the Pauling scale tells you what?
Tells me how badly an element wants to take electrons from something else. Okay? So that's what this scale tells us. Each individual element is assigned an electronegativity value. And that value tells us how much does it want to take electrons from something else. So can you find here what's our most electronegative atom? Fluorine. Right? Fluorine is our most electronegative atom. It wants to take electrons from anyone and everyone. The reason for that is because it has 7 valence electrons in a pretty low energy level, right? It's close to the nucleus. So it wants to take electrons from anyone and everyone. Okay? So now when we start determining are things ionic bonds or are they polar covalent bonds or are they non-polar covalent bonds, we are going to start looking at the difference in electronegativity of the two things that are bonding. Okay? So let's draw a little diagram here. Let's see, bonds over here, and then electronegativity. Electronegativity difference over here. Okay? We're going to do some examples of this. I know it seems a little abstract still. That's okay. All right. If it is a non-polar, non-polar covalent bond, that means they are shared evenly. If it is a non-polar covalent bond, we have an electronegativity difference between 0 and 0.3. Okay? So what that means is that when two things bond and their electronegativity difference is very little, right? That's going to say like our tug of war is very even, right? They're both pulling on the electrons with about the same energy. So that's going to result in a non-polar covalent bond, right? We have to get into our heads that non-polar means shared evenly, okay? If it is a polar covalent bond, polar covalent, I just really can't spell today. Covalent bond. That means our electronegativity values are differing from 0.3 to 1.7. Okay, so that means they're sharing electrons, but they're not sharing them evenly, right? One of them has pulled the electrons a little bit tighter to itself within that bond. Okay, and the last type of bond is just an ionic bond, where we said it was a give and take of electrons. This means that they're sharing so unevenly, one of them actually pulls the electron off the other one, right? That's what we talked about very first, is that one gives up their electron to the other. That's what we're talking here. So if we've got an electronegativity value of greater than 1.7, okay?
And that means like difference.
The difference, right. We're looking at the difference between these two values. And I want to figure out, well, what type of bond is that going to be? Okay? These come right out of your textbook, right? These are just talking about the differences right here are from your textbook. The electronegativity values come from here. So let's go ahead and try one. Let's look at the what type of bond will occur between hydrogen and sulfur. Hydrogen and sulfur. When we draw a bond, we draw it with a line right between them like that. Okay, we're going to get to there and what the diagram looks like. But when you see a bond, a line drawn between two elements, that means those two things are bonded. So let's look at the difference between the electronegativity values of hydrogen and sulfur. What's hydrogen's value?
2.1.
2.1. And what's sulfur's value?
2.5.
2.5. So all we're going to do is take bigger minus smaller. Right? It's not going to come out negative. All we want to find out is what's the difference between those two values. So the difference equals 0.4, right? The difference in their electronegativity means that it has a value of 0.4. And so what type of bond does that fit into?
Polar.
It is a polar covalent bond. Okay, and now I want you to take it a step further. Which of those two elements is going to be pulling the electrons tighter? Sulfur. Good. How do we know that? Well, okay, that doesn't make a huge difference. This is what makes the difference. Which one electronegativity is higher? Sulfur. Right? It does have to do with valence electrons, but you can tell for sure just based on its electronegativity value.
Wait, what do we know about like the positive favor or I'm confused?
Right, so the question we're answering now is, since we know the electrons in this bond are not being shared evenly, we're trying to figure out which one has the electrons closer to it. And that comes to us from figuring out which one has a higher electronegativity value. If they're both the same, it would be a nonpolar covalent bond, which means they would be shared evenly. Yeah. So what if I had to look at a bond between sulfur and chlorine? Let's look at that one. Sulfur and chlorine. Sulfur we said was 2.5. What do we see for chlorine here? 3.0. So the difference is going to be 0.5, which means what type of a bond is that? Polar covalent. And then which one of them is going to be more electronegative? Which one's then keeping the electrons to themselves? Chlorine. Right? So we said that even though in the last example sulfur got to pull the electrons closer, it depends on what it's bonded with. Right? In this case, chlorine got to pull them a little bit tighter. Okay? What if, last one here, what if I examined a bond between hydrogen and hydrogen? Do you have to do the math with that? The difference has to be 0, which makes it a non-polar covalent bond. Right? Non-polar. Think of it as a tug of war, right? They're both going to be pulling on those electrons with equal force, so the electrons are going to be distributed evenly within that bond, right? They're shared evenly within that bond. Yeah, in polar covalent bonds, we're still sharing them. You get to count them as your own, I get to count them as my own, but you might hold them a little bit closer to you than me. Okay. Does that make sense?
Yeah.
Okay. All right, let's look at covalent bonding in a little bit more detail. Okay, we said that in covalent bonding, we share electrons, right? Covalent bonds, we share electrons, okay? Let's remember, how many electrons do they want to be made whole? To feel complete, how many do they want?
8.
Good, they want 8 electrons. What is that called? There's a name for it. They want a complete shell or... octet. Have you heard that word before? We might not have brought that up yet. They want a complete octet. Okay? Why do you think it's called octet?
8.
Yeah. Oct is the prefix for 8. So when we say they want a complete octet, that means we want them to have 8 electrons that they can consider their own. Right? Sharing them and considering them their own. So we have something called the octet rule. And that's really all that it says. The octet rule says each atom wants to share electrons so that both atoms contain 8 electrons in their outer shell. Okay. We want both of them to be able to consider that they have 8 electrons in their outer shell. That's called the octet rule. Now, there are exceptions to the octet rule. There are some atoms that are perfectly happy having only 6 electrons in their outer shell, or whatever. We're going to really focus on ones that follow the rule and get good at those first, and then we'll start exploring some things that have exceptions to that rule. When we draw bonds, we draw them using something... Drawing bonds, we draw something called a Lawis structure. Lawis structure. Okay, and that's really what our goal is for today, is to learn how to draw two-dimensional pictures of chemical compounds, right? We're going to learn how to draw pictures of chemical compounds and what they look like and show their electrons and show how they bond and where they bond and all that kind of stuff. Okay? So when we draw them, we're going to draw them using something called a Lewis structure. We need to remember when we're drawing things and when we're bonding things, we are only dealing with the electrons in the outermost shell. What are those electrons called? Valence electrons, right? When we're dealing with electrons, like let's say I'm dealing with magnesium. How many valence electrons does magnesium have? 2, because it's in group 2. We got to remember that, okay? It's in group 2. It's got 12 total electrons, but I don't care about the 10 in the lower shells. I only care about the 2 in the valence shell because those are the 2 that are available for bonding. Does that kind of make sense? Okay, good. So let's look at Lewis structures. You can draw Lewis structures of individual atoms or of bonded atoms. We're going to know how to do both. Very rarely do we draw individual atoms, but I'll just show you what it looks like. So let's look at the Lewis structure for fluorine. Tell me, how many electrons does fluorine have? How many valence electrons? 7. So when we draw them, we give each element 4 basic sides, right? Top, bottom, left, right. And when we draw them, we're going to draw them 1 on each side. 1, 2, 3, 4. Then we go back and double up. 5, 6, and 7. The order in which you draw them really doesn't make a difference, right? Realistically, we want to see 4 distinct sides. That part is important. But the order, if you draw them in, is not that big of a deal. Like in orbital diagrams, it was a big deal, the order you put your electrons in. This one, not as much.
How can you tell that fluorine has 7 valence?
Because it's in group 7 or 17, right? Oxygen is in group 6 or 16, so it has 6 valence electrons. Nitrogen's group has 5. Carbon's group has 4. Boron's has 3. Beryllium's group over here has 2 and 1, right? That's something we have to know the patterns of the periodic table with.
So can you switch the if you
Yeah, it doesn't matter. Like this could be the same diagram. 1, 2, 3, 4, 5, 6, 7, right? It doesn't matter where the lone. Yep, as long as it has 7. But you can't just put it in circles all the way around, right? They got to have 4 distinct sides. All right, so let's look at, here's fluorine, okay? Let's go ahead and take a look at what it means to bond with another fluorine, right? Here's one, here's another. 1, 2, 3, 4, 5, 6, 7. Okay, so if I'm going to come along and bond these 2 fluorine atoms, what type of bond would you expect they would have? An ionic, a polar covalent, or a nonpolar covalent? Nonpolar covalent. So let's see. I'm going to slide this guy over and bond. Okay, these 2 electrons right here are contained in a chemical bond, a covalent bond. More specifically, a nonpolar covalent bond. Okay, let's go ahead and write this part down. Each bond contains 2 electrons, 1 from each party, right? 1 from each atom has to be contributed to that bond. So in order for something to two elements to bond, 1 electron has to be given from each, and that forms a bond, a single bond. Okay? And so now we've got these 2 electrons that are shared between fluorine. I'm going to redraw them with a line. Okay? So a bond contains 2 electrons and is pictured with a line. Right? That's how we draw a bond, is that there's just a line between those 2 things. Okay? Yeah, we leave the rest of the dots on. That's a good question. Okay, so now, yeah, go ahead, Nora.
Is it 2 electrons?
Ionic bonds would contain 2 electrons as well. Yep, good question. So now I want to check a couple things here. I want to look over a couple things. We said each fluorine came to the table with 7 electrons. Would you agree? So now I want to count. Okay, here's 2, 4, 6. How many electrons are right there? 2. So that gives me a total of 8 electrons so far. 10, 12, 14. Did we lose any electrons along the way? Did we gain any electrons along the way? No, that would be a problem if we did, right? Our Lewis structure has to have exactly the same number of electrons at the end as what we started with. And in this case, each fluorine brought us 7. Excuse me. So our final structure at the end should have 14. Second thing we have to look at is, does each element have its octet rule satisfied? Okay, each element wants to have 8 electrons counting as its own. So let's look at the blue fluorine. 2, 4, 6, and then it gets to count the 2 shared electron as its own. So that counts as 8. And then we take a look at pink. 2, 4, 6, it gets to count these as its own as well. And that means each of them have 8 surrounding them, but in total, we only have 2, 4, 6, 8, 10, 12, 14. Does that make sense? Things here. These leftover electrons, these guys right here, 1, 2, 3, 4, 5, 6 of them. Those groups, this right here is called a lone pair. Kind of a depressing name, but that's what it's called, right? It's a lone pair. Why do you think it's given that name? It's not bonded, right? It's not bonding with anything. It's a lone pair. Any electrons that are not contained in a bond have to be in a pair. Electrons cannot exist in a single. That's important for Lewis structures. You'll see that as we go. Electrons will not exist as a single, ever. If it's not in a bond, it's got to be in what we call a lone pair. Okay? We'll show you how that kind of works out here in a second. But covalent compounds will always have even number of electrons for that reason. Okay? So, how many lone pairs do I have in this structure?
6.
6. Okay, I have 6 lone pairs. 1, 2, 3, 4, 5, 6. Okay. All right.
Wait, so if it's not in the lone pair, it's not.
Let's try some examples. I'm going to give you some rules for drawing Lewis structures, or steps for drawing Lewis structures that you're going to have to reference. So let's get some space for you to draw these steps for Lewis structures, and we'll dive in. Okay? So number 1, label these as steps for drawing Lewis structures. All right, number 1. It's going to go a little bit out of order than what I did on my drawing, but it'll make the most sense, okay? So number 1 says count the number of valence electrons. Count the number of valence electrons in the compound. Okay, all of those valence electrons need to be represented in the diagram. Like in fluorine, we said they each brought 7, so they needed to have 14 in our diagram, and that's what we had. All right, now we're going to do that as step 1. Step 2 is arrange the atoms in what we call the skeleton. Okay, and I'll break that down in a little bit here. Okay, arrange the atoms in what's called the skeleton. Okay, all that means is if I were doing F2, I would have just listed them next to each other without electrons, right? The skeleton is just the elements laid out with no electrons in here. Okay, so there's a couple little side things here for the skeleton. If you ever have carbon, as part of your molecule, it goes in the center, okay, or it's called the central atom. Okay, if you have carbon, it goes in the center.
The center of what?
Like of our skeleton. So let's say if I had a molecule CH4 I was trying to do this for, my skeleton would look like this. C, and then I draw my H's on each side of it before I put in my electrons. That would be my skeleton of CH4. Does that kind of make sense? No electrons drawn in. We've got hydrogen spaced out evenly around it. That's my skeleton for this molecule. Okay? What questions do we have about that? Okay. If you don't have carbon, then your least electronegative atom goes in the center. So if you don't have carbon, the least electronegative ran out of room there. Least electronegative element goes in the center. Okay, so let's say we have this molecule, PCl3. I'm going to take a look at my Pauling scale. Between phosphorus or chloride, which of those is least electronegative? Phosphorus. Okay, so if I draw my skeleton of that, I'm going to put P here, and then I just spread the chlorines out evenly around there. There's only 3 of them. I want to spread them out as evenly as I can. Okay, if there's 2 of them, I'm going to put them 180 degrees apart. If there's 3 of them, I put them, 1/3 apart, whatever. But that's what it would look like. Okay? Okay, last rule here is that hydrogen never is a central atom.
So that means it doesn't go.
It never goes in the center, ever.
How come?
It only has 1 valence electron. So there's no way it could ever bond to more than one thing. So it could never go in the center.
I thought it has 2.1.
It's got a 2.1 electronegativity, but if we think about its valence electrons, it only has 1 electron to give. So there's no way it could go into the center because it could only ever bond to one thing. Okay, that's important. All right, number 3. Bond the central atom to the outer atoms and complete the octet. Octets. We'll say it for all of them. Complete the octets. All right. NH3. NH3. First step is going to be to count the valence electrons. You have got to know group 1 has 1 valence electron, group 2 has 2. That can't be something that you're constantly having to look up. You got to remember that, okay? It goes by their group number. So, nitrogen is in group 5 or 15. So it has 5 valence electrons. And then how many does each hydrogen have?
1.
It each has 1, so that means a total of 3. So that means I've got 8 electrons I need to represent somewhere in my diagram. 8 electrons. What did we say this number was always going to come out to? It's always going to come out to be even, right? So you got to make sure we're looking at that as we go. All right, now second step's going to be to draw my skeleton. Which element do you think should go in the middle, nitrogen or hydrogen? Nitrogen, right? You also should just think about, like, if there's 1 of one element and 6 of the other, don't you think the one that has 1 of it should go in the middle? That type of thinking will help you too. All right, so nitrogen here, I'm going to draw my H's just spread out around evenly, okay? So there's my skeleton, just like that. All right, next step is to bond the central atom to each. Okay, how many total electrons have I used here? I've used 2 in this bond, 2 in this bond, and 2 in this bond. So that means I've used a total of 6. That means I've got 2 electrons left to do something with. Okay, I want to check their octets to see if they're complete, right? Hydrogen, we said, doesn't really get an octet because it's only got 1 valence electron. Hydrogen will really only ever get 1 bond. That's it. Okay, but nitrogen has 2, 4, and 6 electrons around it. How many does it need to have? It needs to have 2 more. It's got to have 2 more electrons. And luckily for me, I've got 2 more electrons I need to put on my diagram somewhere. So all I'm going to do is add them as a lone pair. I don't add them 1 here, 1 there. They have to be paired. So I'm going to pick a spot between 2 bonds and add them. Okay, you could have also put them here. Or you could have also put them here, right? It doesn't really matter the location on right now about where they go. But here's some things that you can't do. We don't put them in the same zone as a bond. And we don't separate them. Okay, so we put them as a pair somewhere between those bonds. Okay, so now I go check. I've used 2, 4, 6, 8 electrons, which is exactly what I wanted. Okay. I want to break this back down just a tiny, tiny bit here. Remember, nitrogen came in with 5 electrons. 1, 2, 3, 4, 5. Each hydrogen came in with 1. So as I'm looking at how they share electrons and what that looks like, these 2 would form a bond, these 2 would form a bond, these 2 would form a bond, and then that's what I'm left over with is a lone pair. Okay, do you kind of see how that comes together? It's not super efficient to draw out the diagrams of each individual atom, but at the beginning that might be helpful, right, to see where those electrons are coming from. Yeah, Faith. Okay, if nitrogen brought 5 to the table, it's got 1, 2, 3, 4, 5 electrons still around it, right? That's pretty good for a central atom. It wants to kind of be, or keep those electrons that it brought kind of around, okay? All right, let's try H2S. Anybody name that molecule for me? Hydrosulfuric acid, good. All right, let's count our valence electrons. Hydrogen gives me 1 each, so that's 2, plus sulfur gives me 6, so I've got 8 electrons again here that I need to represent. Is that green hard to see in the back? I'll just refix it. Is that better? Yeah. H2S. So hydrogen each gave me 1, which is 2, plus 6. So I've got 8 electrons I got to take care of. Which is going to be my central atom here? Got to be sulfur. Okay, so here goes sulfur in the center. And then I've only got 2 hydrogens, so they got to go 180 degrees, on either side of sulfur. You could go top and bottom if you want. That's fine. I just usually don't. Okay, so we've got our skeleton built. We've got our valence electrons. Next step is going to be to bond the central atom to the outer atom. So here's 1 and 2. So how many electrons have I used so far? I've used up 4, which means I've got 4 electrons left I need to do something with. Can I add another bond here to hydrogen? No. Yeah, no, that won't work because hydrogen only gets 1 bond. So I've got 4 extra electrons, so I'm going to put 2 and 2, right? 2 sets of lone pairs onto sulfur because sulfur wanted 8, but it only had 4 around it. Now it's got 2, 4, 6, and 8. Okay, what questions do we have with those Lewis structures? Okay, we're going to break away from hydrogen a little bit. Hydrogen's an easy atom to work with in Lewis structures because it only gets 1 bond. Now let's look at one that doesn't have hydrogen. PCl3, right? We gave this example a little bit ago. PCl3. All right, let's add up our valence electrons here. Phosphorus gives me 5. Chlorine gives me 7, and there's 3 of them, so that's 21, which means I'm looking for a total of 26 electrons here I'm going to have to take into account in my structure. Did we do that math right? 5 plus 21, I think, is 26. All right, so I'm going to put phosphorus in the middle, and I'm going to lay out chlorine spread out along the way. Okay? Questions about how I built that skeleton? Okay. Now I'm going to bond my phosphorus, my central atom, to each of my outer atoms. I don't bond the outer atoms to each other, right? Everything just goes to the center. So I've used up 6 electrons there. That leaves me with 20 left over. So that's a lot, right? We're used to having like 2 electrons left over. We've got 20. So we want to start checking the octets. Okay, and my advice is going to be to check the octets of the outer first, and then we move into the center. Kind of leave the center atom as your last one to adjust. My octets now for each individual. So chlorine, this chlorine wants to have 8 around it, but right now it's only got 2. So how many lone pairs do I need to add to that chlorine? I need to add 3 lone pairs. 1, 2, 3. Because now this individual chlorine has 2. Oh, sorry. My iPad switched over. This individual chlorine has 2, 4, 6, 8 electrons around it, right? It gets to count both the electrons in the bond for itself. So that means I've used 6. I've got 14 left over. I'm going to do the same thing probably down here, right? 2, 4, 6. Now I've got 8 electrons left. Now I'm going to go 2, 4, 6. So now I've got all my chlorines happy, but I've got 2 electrons left over. All of my chlorines have complete octets. Does my phosphorus have complete octets? No. So what do I need to do? I add a lone pair, right? Let's start using the lingo. I add a lone pair to phosphorus. You can go anywhere between those sets of bonds, and now I've got a completed structure. There's none left over. Yeah, Kevin, sorry, did you have a question? All right, so I'm going to go count. Chlorine, 2, 4, 6, 8. So it's happy. Phosphorus, 2, 4, 6, 8. Excuse me, it's happy. 2, 4, 6, 8 for this chlorine. 2, 4, 6, 8 for this chlorine. And then I would recommend just recounting all my electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Right, to double check. Yeah. C2H4. Do you see an issue here? Yeah. What do you see as your problem?
We'd have 2 central.
2 central atoms. Bingo. Right? No, because it's a covalent. Yeah, good question, though. Good question. In an ionic, yes, you would. Covalent, no. Okay, so yeah, we're going to have multiple central atoms, which is not a huge deal, but let's go ahead and count. Carbon each gives me 4 times 2, which is 8, plus 4 means I need 12 electrons in my structure. Okay, so we already looked at this issue. We've got 2 central atoms, which is not a huge deal. We draw them there, and then we draw the H's just surrounding. Right? The 4 H's are split between those 2 carbons. Okay? I'm going to draw my bonds. I first have to bond the central atoms to each other. Then to each of the outer. Okay, so how many electrons have I used so far?
10.
I've used 10. So I've got 2 electrons left over here. Do I ever add lone pairs or anything else to hydrogen? Right, hydrogen only gets 1 bond. So now I go look at carbon. Okay, well, could I do this? Add a lone pair right there?
No.
That makes this carbon happy, but it doesn't do anything for this guy, right? Yes, perfect. What I want to do is, instead of just making 1 carbon happy, I want to make both carbon happy, and I would just move these 2 electrons and slide them into a bond. Right? The electrons that are left over, they are going to become now a double bond between carbon. Okay? So this carbon gets to count 2, 4, 6, 8 as its own. This carbon gets to count 2, 4, 6, 8 as its own. And then in total, we've used 2, 4, 6, 8, 10, 12. Let's see what you do with this. How do you think we should handle this that has a charge? How do you think we handle that?
Have noticed subtracted from the
Good. Okay. Do you think with a +1 charge, would we add an extra electron or would we take away an electron?
add an electron.
Take away, right? Because if we've got a positive charge, that means we're short on the amount of electrons we should have. So 5 plus 4 gives me 9, but we know it's got to come out to an even number. This means that we need to take away an electron. take away an electron, which means we need to have a total of 8 electrons in this structure.
Wait, why wouldn't you want it to be 10 electrons? Because if it's...
When you have a charge, not only does it change your valence electron numbers, you also have to add these brackets and the +1 to tell us that the charge is distributed over that molecule. Okay, that's kind of what it's looking like here. Okay, so when you have a charge, you add the brackets and you put the charge outside the brackets just like that. Okay. All right, I'm going to give you 2 now to try on your own. Okay, that's how you handle it with the charge. Let's try PF3. My bad. PF3, not PF4. My bad. PF3, not PF4.
Where is that 5 and 21?
Well, phosphorus has 5 electrons. Each fluorine has 7, so that's 21.
Oh, never mind. Pretend I didn't ask. No.
It's okay.
So, because it has a negative charge, we would need to add an
Right,
electron.
correct.
So, I'm pretty sure I started off to the right start, but it is going to end up being
Yes, yes, but fill the octets at the outside first, but yes, you're on the right track. But you haven't used, you've used 2 more here. So that's 2, 4, 6, 8 you've used, not 6. You have 18 electrons left.
18.
You know,
I'm still confused.
this is 2 electrons here, 2 electrons there, 2 electrons there, and then that's 2 more. So you used up 8, plus this one is just 10, but.
Oh, so I need to try and make it 26.
Right.
Do you have a question?
Uh-huh.
18, 19, 20. So, if it's a unit, what would you No, it's not. Correct. 18, 19. Yeah, that's 23. 5 plus 18. Oh, okay, but you have to run a charge. Yeah, you need to add the charge and then you get 24. Yeah. She got it. 4. No, because it's a negative charge, you add 1. So it's just like... Thanks, Hamilton. Wait, so did I do it right or wrong? You did 24? No, 24. I thought you were... It's 24. Okay. It's 22, that was mine.
Uh-huh.